Ladies and gentlemen, I hope everyone is doing great today. For today's presentation on the thermohaline circulation and its role in ocean mixing, hosted by Group 6. Before we start our presentation, I would like to introduce our team members: Navin Raj, Mohammed Sahari, Mohammed Karol Aslan, Mohammed Izul Hakim, Nouralia Saifika, Noor Maisara, Noor Aina Amir. Let's dive into presentation.
Hi guys, my name is Noor Aina. I will be presenting the thermohaline circulation. An essential mechanism in the marine system of Earth is thermohaline circulation, which is fueled by changes in water density brought on by variations in salinity, halin, and temperature, thermal. The global climate, nutrient cycling, heat dispersion, and ocean mixing are all impacted by this world-scale circulation. Comprehending the complexities of oceanic and atmospheric interactions, and forecasting the effects of climate change necessitates an understanding of thermohaline circulation. Next is ocean mixing. The Earth's temperature and marine ecosystems are greatly affected by ocean mixing, which is mostly dependent on thermohaline circulation. The redistribution of heat is one of the circulation's most important roles. Thermohaline circulation affects weather patterns and serves to moderate global temperatures by moving warm water from the equatorial regions to the poles and sending cold water back to the tropics. Preventing drastic temperature swings and preserving a stable environment depend heavily on this heat transfer process.
Hi, my name is Sarah. I will be presenting about the physical characteristics and processes involved in thermohaline circulation and its role in ocean mixing. Thermohaline circulation begins in the Earth's polar regions. When ocean water in these areas gets very cold, sea ice forms. The surrounding seawater gets saltier, increases in density and sinks. Winds ocean currents in the upper 100 meters of the ocean's surface. However, ocean currents also flow thousands of meters below the surface. These deep ocean currents are driven by differences in the water's density, which is controlled by temperature, thermo, and salinity, haline. In the Earth's polar regions, ocean water gets very cold, forming sea ice. As a consequence, the surrounding seawater gets saltier, because when sea ice forms, the salt is left behind. As the seawater gets saltier, its density increases, and it starts to sink. Surface water is pulled in to replace the sinking water, which in turn eventually becomes cold and salty enough to sink. This initiates the deep ocean currents driving the global conveyor belt.
Hi guys, my name is Izul. I will be presenting about the processes involved in thermohaline circulation. First one is deep water formation. Deep water is formed where the air temperatures are cold and where the salinity of the surface waters is relatively high. The combinations of high salinity and cold temperatures make the water denser and cause it to sink to the bottom. And next is downwelling and upwelling. Downwelling happens when cold, dense water sinks from the surface to deeper layers. It occurs primarily near the poles and in regions where water becomes denser due to cooling or increased salinity. Upwelling, on the other hand, involves the rising of deeper water towards the surface. This occurs in various locations, influenced by wind patterns and coastal geography. Moreover, global conveyor belt, the Great Ocean Conveyor, models global deep and surface water flow. Warm currents move poleward, cool, sink, and return equatorward as deep currents. Mixing and redistribution, thermohaline circulation, THC, is driven by heat and freshwater fluxes across the sea surface and the mixing of heat and salt. The term describes this driving mechanism. The last point is wind-driven circulation. Wind stress induces a similar circulation pattern in each ocean, forming gyres. Subtropical gyres stretch from the equatorial current system to around 50 degrees latitude, while subpolar gyres extend poleward from there.
Hello guys, my name Navin Raj. I will be presenting about the concept of thermohaline circulation and the factors driving it, temperature and salinity. Key components of thermohaline circulation: temperature, thermo. More frigid water is denser than warmer water. In polar regions, surface water becomes denser and sinks as it cools. In equatorial regions, warm surface water remains on top due to its lower density. Salinity, haline. Salty water is denser than fresh water. Evaporation increases salinity and density. As an example, consider the Mediterranean Sea. Freshwater input reduces salinity and density, such as from river outflows or melting ice. Next is drivers of thermohaline circulation. Density differences, salinity and temperature differences create density variations. Dense masses of water sink, while light water masses rise. Formation of deep water masses. The Northern Atlantic deep water is formed by cooling and increased salinity from evaporation in the North Atlantic. Antarctic bottom water is formed through intense cooling and brine decline during sea ice formation in the Southern Ocean. Ocean mixing, the sinking of dense water masses at high latitudes. Upwelling of nutrient-rich waters in specific regions. Examples include the Indian and Pacific Oceans. Water masses move horizontally along density gradients. The global impact of thermohaline circulation. Heat distribution transports warm water from the equator to the poles. Helps regulate global climate trends. Nutrient cycling transports nutrients from deep waters to the surface, promoting marine life. Enables the biological pump, which sequesters carbon dioxide. Oxygen distribution transports oxygenated surface water to deeper ocean layers. Supports deep-sea organisms. Moreover, discuss its role in nutrient distribution and global heat transport. Bringing nutrients to the surface. Deep ocean waters are high in nutrients such as nitrogen dioxide and phosphate. These nutrient-rich waters rise to the surface due to thermohaline circulation, which includes rising and mixing processes. Enhancing biological productivity. Phytoplankton thrives in surface waters where nutrients are abundant. Phytoplankton is the foundation of marine food chains, sustaining diverse ecosystems. Facilitating the biological pump. Thermohaline circulation is related to the biological pump that transports carbon dioxide from the atmosphere to the deep ocean. Phytoplankton ingest carbon dioxide during photosynthesis and, when they perish, their organic matter sinks into deeper layers, storing carbon. In a nutshell, role in global heat transportation. Heat redistribution from the equator to the poles. Thermohaline circulation distributes heat from the equator to the poles. Ocean currents transport warm surface waters towards the poles. Influencing climate patterns. Thermohaline circulation has an impact on global climate patterns by redistributing heat. The Gulf Stream warms Western Europe, resulting in milder winters. Regulating ocean and atmospheric circulation. Thermohaline circulation is responsible for large-scale oceanic and atmospheric circulation patterns. Changes in thermohaline circulation can disrupt regional climate and weather patterns.
Hi guys, my name is Mohammed Zahari, and I will be presenting the examples such as the Atlantic meridional overturning circulation, AMOC, and its influence on marine ecosystems. For the first point is Atlantic meridional overturning circulation, AMOC, controls temperature patterns in the North Atlantic, promotes fishery productivity and marine biodiversity by transporting nutrients. Changes in Atlantic meridional overturning circulation can impact marine habitats and species distribution. Next is the Southern Ocean Circumpolar Current, SOCC, promotes a diverse marine ecosystem, including krill, seals, and upwelling along the Southern Ocean Circumpolar Current, improves primary productivity and supports marine food webs, contributes to global climate regulation by transporting heat and carbon dioxide. The last one is the Pacific Decadal Oscillation, PDO, impacts marine species distribution and fish stock abundance, affects primary productivity and nutrient cycling in the North Pacific, can impact ecosystem resilience and vulnerability to environmental change.
Hi guys, my name is Mohammed Khairul Aslan. I will be doing the conclusion. For the conclusion, I have ecosystems and conservation to be present. The first one is ecosystem. The thermohaline circulation is driven by differences in temperature and salinity, and it also circulates ocean water globally. Colder than saltier water will sink, while warmer and less salty water will rise to the top. This creates a global conveyor belt, and this process is essential for transporting nutrients and oxygen to support marine ecosystems and regulate Earth's climate. And the next one is conservation. The thermohaline circulation is the movement of the global oceans driven by variations in temperature and salinity. Cool and salty water is denser and will sink, while warmer and less salty water will rise to the top. This circulation ensures the conservation of mass and energy in the ocean and redistributes heat and nutrients. It also plays an important role in regulating Earth's climate and marine ecosystems.